Hi everyone, welcome. So we're going to be onboarding on our journey for the class EE274 on data compression, theory and applications. And today it's all going to be about introduction and logistics, and then we'll just deep dive into the material towards the second half. So this is your course staff. We have Professor Tsachy Weissman sitting right there in the cool jacket. We have Shubham, who is also there, and he'll be taking the second half of today's lecture. I am Pulkit, and I'll also be part lecturer. And then finally, we have our awesome TA sitting there, so for any class-related material. We also have Kedar, who was the instructor from last year, who will be helping us from the sidelines. So you have another extra resource at your disposal. Okay, so let's just dive in. So this is like a curve which you might encounter at some point in your life, okay? The y-axis here is the data volume in zettabytes, and the x-axis is the year. So this is like the volume of data which has been created and replicated worldwide, okay? And it has a trend which is like, okay, it's exponentially increasing. But like, and this kind of curve kind of shows up in all sorts of applications. But like, what does these numbers really mean? Like, right? Like, what do they reflect? More precisely, like, what exactly is a zettabyte? Like, why should I care? Right? So let's try to get some sense of these numbers. Okay. So let's start with a megabyte. So megabyte really is 6 zeros behind that one. And it's roughly the space which is occupied by a lossless image in your smartphone. So this is the image of my cousin's dog, Ace, and the unfiltered version of it was taking approximately a megabyte on my phone. Okay? Continuing, as you add 3 more zeros behind it, you get a gigabyte, which is approximately the space which is occupied by a typical 4K video of a few minutes duration. And this was supposed to stream automatically from YouTube, but it was basically a video clip of your favorite anime. Okay? Continuing, if you add 3 more zeros behind it, now we start talking about terabytes. Okay? And this is something which I'm sure at some point you might have encountered when you went on to buy an electronic device from your favorite manufacturer. This is what that manufacturer kind of charges you for each extra terabyte storage. Okay? And you need that extra terabyte storage year after year, right, to store all those photos and videos which we just talked about. Okay? So at this point, with the, I guess, 12 zeros behind, we are already at the typical storage which is available on your laptops as of now. Okay? Let's continue. Add another 3 zeros. And what we get is actually a petabyte. And at this scale, we are now talking about the databases which are stored by like really even medium scale companies as of today's standards. It's actually the de facto cloud storage unit. So if you have ever heard of AWS S3, Google Storage, Azure, like all of these are cloud storage services where you can store your data. And when you talk about like how much data is being stored by these companies, you typically talk in units of like petabytes. And again, a petabyte, like at each of these steps, we have been adding 3 orders of magnitude behind what we have been seeing before. Okay? In fact, like a cool fact, like Meta was roughly generating more than a petabyte of data to be ingested every day. Like every day. Okay? And so at this scale, basically what you're talking about is millions of dollars of management. If you are a business person from a company managing this data, or if you are a team at AWS S3 or GCS, you are like by managing petabytes of data, you're talking about millions of dollars of data in management under your control. Okay. So far, so good. Let's add another 3 zeros. Because why not? So now we are at 1, 2, 3, 4, 5, 6. 6 times 3 zeros behind the 1 of the bytes which we were talking about. And what you get is an exabyte. And this is roughly the estimate of data which is being transferred over the internet daily. Every day. This is the amount of bytes you are like sending to and back. Okay? And this finally leads us to what this number zettabyte really is. Right? 1 zettabyte is actually 3 orders of magnitude over what I just talked about, the last thing. So I want to wait a second, and I want you guys to really appreciate these are like 21 zeros. We started with just 6 zeros behind one of your photos. It's not multiplied by 2. It's multiplied by 10 raised to 15 from that single photo which you are very carefree to capture on your phone, right? And this zettabyte is what's being shown on this curve. So when you went on from, let's say, 2 zettabyte around 2010 to something like 64 zettabytes, it's actually 62 of 21 zeros of data added in the world. Okay? So clearly managing this much amount of data is an issue. Like, data is growing at an exponential scale, and this is a serious problem in all applications, right? You have to somehow manage this data. You have to somehow understand this data. You have to use this data to drive your business, or you have to use this data to really come up with the cool machine learning applications if that's what you care about. Okay? So this clearly says that like there is a need. Like if this continues, like we won't just have enough space to store data for ourselves, right? So you have to worry about the storage at this point. Okay? But interestingly, it's not just about data at rest. It's not about just, okay, I collect this data, I store it at one place, and life is great if I can do that. It's also about the data in motion. Once you store this data, you will use it for 1,000 different applications, for analytics, for just transferring data to your friends, so on and so forth, right? And that's also a very big issue. Like, you have to move this data around. So this is like an estimate of like the proportion of internet data traffic around, I think, 2021. And here, what you see interestingly is videos are taking roughly 50% of your internet data traffic daily. And this is a serious issue. How can I convince you that? Back during COVID, Netflix got a technical request, like legal request from EU to reduce its bandwidth because they were just not able to support it. They were not able to support the increase in data traffic around their networks. So Netflix was basically asked to either reduce the quality or improve their compression algorithms, improve the compression which they provide, right? And again, like these are just like some conservative numbers of like what you are really streaming when you are watching your favorite show, like how much data you are consuming without even thinking twice about it, right? So these numbers, if you just look at them, like a high definition Netflix stream can use as much as 3 GB of data each hour. Okay, these numbers and the world which we live in is unprecedented, and it's on an exponential growth scale with respect to the data. Okay, great. But the interesting part, as I said about videos and Netflix, right? But it's not just about videos. It's not about any single kind of data. Data compression shows up and is of value wherever you collect data and whatever kind of data you are collecting. So things like text, log files, code, even like if you ever use GitHub, and you do a git pull, this is like a standard message which comes up. So this is, for example, an instance of when I was updating the website for the course. And very interestingly here it says something like compressing objects, right? So if you have never ever actually looked at it carefully, even GitHub, every time you are doing a pull, push, any of those things, you have to compress. Otherwise, you can't really do a version management. You just can't creating copies at every single change, which you are making and committing to your favorite repo. Okay? So this is like working in the background. But not only that, there are like genomic data, emails, all your Google searches, tweets, images, videos, things like EEG, which is like electroencephalogram, like sensor data. Like if you think about like the biomedical applications, the amount of data you are collecting is immense. And again, many times it's not even possible to transmit this data, collect this data, let alone like do any sort of analysis on top of it. Like neural recordings, your multiverse, and not even that, even LLMs and ML models. So if you care about machine learning, like there is a big push for there is a deeper connection between compression and machine learning models. And there is like bidirectional communication in the sense like people have been using machine learning to improve compression, but not only that, compression has been an integral part to understand what's happening in machine learning. So if you are aware what's happening of maybe, I don't know, llama and so on and so forth, you would also know there are all these sorts of quantized models. Like, why do you need these quantized models? Why is everyone after them? Because unless you do that, you can't run any of these things on your favorite devices. Okay? So what I really want to highlight here is like it's omnipresent. No matter what's your application area, maybe you're a bioengineer, maybe you don't care, you're just a software engineer and wants to have the most efficient version management for your softwares, or you're just a machine learning engineer, right? No matter what you do, you will see compression at play at some point during your lifetime. Okay, even more interestingly, your compression, it's filled with trade-offs. It's not really like when GitHub says like, okay, compressed. There were a lot of design decisions which were made in the background. And what we'll teach you in this class is also to understand like how to make these design decisions, right? It's not just about taking a file, right-clicking, compress, and be done, right? It's always about like the trade-offs given your applications, what you really want to achieve. And this is like a curve which we'll see a lot in the, or like variants of it, a lot in the second half, and Tsachy will cover its theoretical aspects too. But basically what I'm showing here on the x-axis is size, and on the y-axis is error. And for those of you who are aware, it's like rate distortion curve, if you would have heard of it at some point in your life. And the basic idea is this, that when you have higher size, you can get away with smaller errors in your files, right? And as you keep decreasing your size, you will have higher and higher errors, right? And this kind of leads to some very interesting trade-offs. And maybe let's get into some of them. Let's try if this works or not. Okay. So now, hello, yeah. Now I'm going to play some audio files for you, and let's just see what you guys feel about them, okay? So this is the first audio file. Okay. I don't know, maybe some of you recognize what was being played. Maybe not. But this is like that audio file at roughly 5 MB. Okay, and that's maybe this point. Let's reduce the size and rehear what this file sounds like. Okay. Any thoughts? Like, was it good, bad, don't care? You have some thoughts? Oh, wait. Shouldn't play. Okay. Anyone? Yeah? You felt the quality went down? Oh, a little bit? Okay. But was it okay? Like in the sense, would you still... Oh, okay. Actually, any other thoughts from the class? So, right? Felt that the quality went down. Anyone else? Any thoughts? Couldn't notice. Sorry, what's your name? Okay. So, here said that he couldn't notice much difference. Great. So we have some difference in opinion here already. And we reduce the file size to something like half. Okay. Let's go down a little further and see how that sounds like. Okay. What about now? Bit worse, but you might still live with it. Okay, that's fair to say. Anyone else, any thoughts? Yeah?
The frequencies are distorted. Like the last one was much more shrill and like unpleasant.
Okay, sorry, what's your name? So here observed that the frequencies went down, and he found that the last one was like a bit shrill, and just like something was off. And again, like the point which I want to highlight is that at this point, you have compressed the file. And even in this classroom, which is really small, the scale of world, we have some difference in opinion, right? Maybe said he can live with 2.5 MB, he doesn't care, is not cool with that. Like even going from 5.3 to 2.5 MB is like, this is my favorite song, I can't hear it like that, right? And when we went down even further, there was again some more disagreements, right? Like, again, like some of you might be okay, some of you weren't. And these are the real trade-offs which you face in real world, right? Like, you have to take a call. Like, if your phone just have, I don't know, a megabyte space left, you can't do anything. You have to go down to that size. But something interesting to note was, even at, I don't know, we reduce it by roughly 5x, the audio quality sounds still okay. Like, if that was the space which you have left in your phone, you might still want to keep it. But let's say if you're streaming it over the Stanford network, you wouldn't like to do that. You would like to hear the best quality, right? Okay. So this was just an example of the audio. Continuing, we can look at the same example for images. So this is like a popular character out there. Just an image of the character. If you don't know, don't worry. If you know, hope you like the show. So it's this is the image stored at 585 kilobytes. Again, let's reduce the size further, and this is at 280 kilobytes. For me, I am okay, right? Let's reduce the size further, and now this is the same thing at 13 kilobytes. Okay, we have reduced the file size by, I don't know, around like 500x, right? And there are two comments, like more or less, I think this is okay. This still captures like the big part of this images, right? Like you can still make out the character. But if you are a connoisseur, or if you really like to watch a lot of movies and like whatnot, maybe you observe that there were like some distortions which started showing up, like ringing artifacts right around here. Okay? And during the class, we'll get into such details. Why these things happen, what are the compressors being used, when you can throw away stuff without introducing a lot of distortions. And this is basically the job of all the big businesses. Like Netflix optimizes its stream so that you can get the best quality, or your favorite streaming provider, right? Same with Spotify. Like if you look at Spotify settings, you would see like whether you want the highest quality or the best data saving mode. This is the curve along which they are basically playing. So hopefully by the end of the class, you can appreciate all these things better technically and be able to understand these trade-offs more intricately. Okay, so I'll wait. Any questions so far? Cool. And so, okay, so this is really the punchline, right? And I'm quoting Tsachy, who's just sitting right behind, because this is where I heard it first from, and I really think this line kind of summarizes the data compression, which is, it's basically the succinct representation of information. Okay, so you're okay to throw away stuff as long as you don't throw away information, or you try to keep basically whatever message being communicated through whichever medium as close as possible to the original one. Yeah. And like we have been saying, like why do we care about compression? I think I'll go through this slide fast because I did show you guys some examples of why you might care about the compression. But basic points have remained the same. So like storage is costly, and like we are generating exponentially exabytes more data, right? More so, it is really purest form of information processing. Compression intricately is related to your signal denoising in a way. You are basically trying to keep the most useful part of the information in whatever thing you are outputting out of this compression, right? And in same way, it's equivalent to communication without noise, right? So when you're communicating, maybe you're adding some noise, you're spending some storage to actually, or some bits to actually spend on those noise. And what compression tries to do is extract the relevant information out of it. Okay? So you also have these compressed representations, which might be very easy to transmit and search on, because now you have thrown away the fluff and kept really the information part of the things. And it can even simplify implementations. For example, if you are working on just the compressed representation instead of like the whole big data, you may not be able to move that whole big data, versus if you're working with a smaller part of it, maybe you can do something about it, right? More so, it has a very fundamental relation to the data modeling, prediction, and even like your favorite ML, so as to say, right? And this is a point which we'll try to drive home at some point, that basically a good compressor is a good predictor, and vice versa. If you basically somehow are able to come up with a good predictor, you can use it for compression, sans some conditions, which we'll talk about, and so on and so forth, right? So it's very fundamentally linked to what you are able to predict. And finally, it is really a very critical building block in today's, like, I would say, any scalable and efficient system. Okay? In fact, my first foray into compression wasn't even through the standard compression thing. I was trying to build an application for brain-machine interfaces, and there was absolutely no way I could have collected that data and transmitted it. Like, it was just impossible. I was working on some eye prosthesis, and I would have burned the eye, like way before I would have been able to collect the data I would need. Okay? So what I'm really trying to highlight is, no matter what application you are into, at some point you might run into compression just as a necessity. Or we have actually sitting in the class, and like in her case, like she used compression as a tool for her application. And that's another way where like you might come up with some of the tools we'll talk in this, you might use some of the tools which we might come in this class in very interesting ways in your application. And that all stems back to all of these things, that essentially it has very deep connection to prediction. It is basically the purest form of information processing. So compression is basically what I want to highlight. It's way beyond, again, right click, compress, zip, done. It is very interesting. In fact, it is so interesting. Actually, let me pause here. Any questions so far? Okay. Yeah, so compression is super interesting no matter what your interests are. Okay? So what I want to highlight is that there is something for everyone who's sitting here. You love theory. You really like to understand the world in mathematical formulations. Compression has very deep connections to information theory. And here it's Claude Shannon, who's like the father of information theory. Okay? For example, I started this presentation with exabytes, megabyte, kilo, like whatever, terabytes, so on and so forth. And all of you were like, yeah, we understand. Very cool, right? Sure. So we are in a digital information age. Everybody know what bits are, what bytes are, right? But basically, it has a very fundamental connection to whatever we have been doing. It has fundamental connection to information. And it's not coincidental or arbitrary that we are talking in terms of bytes. And in fact, we'll cover the basics in this course next week. Most likely, you'll start seeing the exact bits coming up. But if you're more interested, I would encourage you guys to take EE276, which is a specific information theory course, again, taught by Tsachy. Okay. Another interesting question. So take your favorite compressor, I don't know, whichever one you want to pick. Input it a file. I don't know if you have ever thought of it, but why can't I just keep applying it in a loop? Like, whatever output I get out of, I don't know, zip, let me zip it again, zip it again, zip it again. Why am I not able to get to 0 bytes? Like, why am I taking any space? Okay. So actually, very interestingly, apart from the implementation inefficiencies, no matter what you do, there is like a fundamental limit to where you can compress things. And it's very well understood mathematically. And that's where like the entropy term gets introduced, and we'll explain it to you. So funny, if somebody comes to you with their $1 billion pitch and they say we can reduce all the file sizes by, I don't know, 99.999999%, you can turn it down very politely after taking the course. Like, don't entertain. Okay. Another fundamental question is like, for example, which we saw in the audios and videos case, images case, which is, how much can I compress if I'm okay to lose some information? Right? For example, in that image case, we went from 515 kilobytes to 13 kilobytes, right? And we got some quality. Was this the best thing I could have ever done? Could I have done something better? And again, there is like a very interesting, to the core, beautiful mathematical theory for it, which is called rate distortion theory, and you'll understand that there are like fundamental limitations to what you can do there again. Okay? So if you are into theory, there are some very interesting questions which involve compression. Okay. Maybe some of you are from CS here, and you don't care about theory as much, but you get very excited with algorithms, right? Like you want to just, like, okay, there are like extremely elegant algorithms which are involved in compression, right? And we'll introduce some of them in the class. So here's a picture of Lempel and Zip, which is the LZ, and hopefully by the end of this class, you will be like, you will know. So I'm throwing lots of acronyms here at the end. But the hope is by the end of this class, you'll be familiar with them, you'll be conversant with them. You'll be able to talk with your peers and others who work in compression about them and be able to understand these things technically. So for example, there is like existence of universal lossless data compression algorithms, which is like the reason for popularity of all these LZ-based schemes. For example, gzip is an LZ-based scheme. Okay? Even more so, there is like all this usage of transforms in multimedia compression, like KLT, FFT, DCT, and you'll understand why these algorithms and to be able to do these things efficiently is extremely important for compression. And finally, like again, very interestingly, like there are questions like how are numeral systems, like 2 times 10 plus 2 equals to 22, how is this related to compression? And you might find it very surprising, but it is. And you'll learn in this class how. And finally, if you are someone who's like even like a true engineer, who goes right down the assembly code or writes the most efficient software code, you don't really care about the algorithm, you want to optimize to the dot, there are some extremely clever implementations involved in compression. Because as you might imagine, like nobody has the time to wait for your video file to decode in a day if you want to watch your favorite Netflix stream or whatever it is, right? Just absolutely no one has time. And so there are some very extreme clever implementations which people have come through in this. So for example, like I'm gonna just combine this in a single go, which is like, can we cache computations? Very simple questions, right? But if you are someone who has done computer architecture or hardware, like you'll be surprised to know there are like specific hardware implementations in your laptops right now, just for being able to run a video decoder, without which your videos won't run real time on your favorite browser. So people have not only optimized software, they have went on and worked at the level of instruction set architectures to optimize the compression algorithms and theory which just preceded. Okay, this is a fun one. I don't know if you guys have noticed, but if you are trying to go back and forth on YouTube, Netflix, Prime, whatever it is, there is like some smallest delta at which you can go back and forth. Maybe it's 5 seconds, maybe it's 1 second, 2 seconds, depends, right? But notice, like try it after you go home today. Like YouTube, you maybe will have to check, I think it's 5. No, it's 1, I think. I don't know, but some point it used to be 5. And if you go back and forth, you can't go back and forth in units smaller than them. Okay? And that's also very interesting because it comes around from a clever implementation for you being able to stream videos real time. If you don't do that, if you try to give a millisecond level stream, like millisecond level seek for the videos, you won't be able to decompress it real time. And then you'll start seeing the annoying bar, the annoying circle, which everyone hates. Okay, so that's actually a side phenomena which is coming from a clever implementation. And there, basically, you have something called frame groups, IPB frames, which is again something which we'll touch in this lecture at some point. And finally, there are also some interesting data structures which shows up, like suffix trees and BWT transform. In fact, there were like data structures which were designed for compression and now are mainstream in certain places like genomics. Okay? And so really the takeaway of all of these examples is that no matter what you like, there is something fun for you in the field of compression. And in this class, like how this class I would say differs from the other offerings, even at Stanford, is that we'll try to give you a flavor of all these three and like kind of packed in a quarters framework. Yeah. So in particular, the first half of the course, so now we'll get a little bit into the course. The first half of the course would deal with lossless compression, which is like if you don't lose any information. And the second half would deal with the lossy compression, which is like, okay, I'm okay to lose some information. What's the best I can do now? And throughout the course, we'll keep showing you workings of various tools and code snippets. So there'll be a mix of, we'll also show you some theory, some proofs, but we'll also show you like lots of tools and code snippets. So hopefully it will be fun for everyone and you'll try to appreciate the same material from different angles. So this is just course outline. It's also available on the website, but let me just go through real quick. So on lossless compression side, we'll talk about entropy and its fundamental role in compression, like we have been saying, for the, I think till week 2 roughly. And then we'll start getting into the lossless compressors right from week three of the class. And there we'll study like lots of compressors like Huffman, arithmetic coding, asymmetric numeral systems, your LZ, on hopefully by the end of it all, you would have a deeper understanding of how gzip works or how you can do lossless compression much better for whatever application you have. We'll also talk about how you can handle correlated sources, so things like adaptive arithmetic coding. Okay. And this is going to be roughly till lecture 10, so first half of the class. And then the second half of the class will be around lossy compression, where, like I said, I've been saying for some time, we'll talk about rate distortion theory and mutual information. We'll talk about quantization. We'll talk about transform coding, like all these different transforms. Why do they show up? Why do they matter? And then we'll have basically a very deep dive into images. I think roughly 2.5, 3 lectures almost, where we'll talk about image compression because a lot of these principles kind of tie together there. In particular, we'll talk a little bit about how JPEG works, BPG works, as well as how ML in particular has been used to improve compressors. So like the new age compressors, people have been trying to incorporate all these new ML findings. So we'll have a dedicated lecture on that, on like how you can do learned compression. And finally, we'll kind of wrap it up with like video compression, because as I think I've been highlighting, video is a really big part of your streaming pipeline and some role of like human perception and lossy compression. And the hope is by the end of this, what I'm showing here on the right is just like there's this tool which gives you properties of a compressed file, in this case, a JPEG file on my laptop. And there are a bunch of things. And maybe some of you are familiar with some of them, maybe all of them, maybe not. For example, things like what does this encoding process means, baseline DCT, Huffman coding. What does this YCBR sampling means? What does this color space mean, right? Things like this. And hopefully by the end of all of this, you would be able to appreciate these things and understand and make through. Okay. And then finally, it's a rich field. We are only going to touch like the tip of the iceberg, but there are like a bunch of interesting extensions, which we would encourage you guys to play with during the course project. So I don't know, like I've been saying, so if some of you are really proficient in ML and that's what you want to do, you'll come talk to us and we'll try to frame a very concrete problem for you around, let's say, compression and neural nets. Maybe it's not just about using ML, but also like you have this big neural nets, how do you apply compression to them, right? So it's a two-direction thing. You can use ML for compression or you can compress your ML models to improve efficiency. So this is just like one of the examples. Or again, like I think I said at some point, like, so if some of you have architecture and hardware background, maybe the way you can dive deeper into this material is by picking up one of the algorithms and trying to implement it in your favorite favorite low-level language, right? So it's going to be up to you, but there are like lots of topics. And in particular, I'll say like, so we are going to organize something called Information Theory Forum, and it's going to have guest speakers, basically, like leaders in their field, also going to come and talk to us about various different topics. So think of them as like complementary aspect to the course. Okay, let me pause here for a couple minutes because after this we'll just go into the logistics of the class. Any questions so far? Any comments, thoughts? No? Cool. I think we should move on to the next part, and I think I would like to just end here, shamelessly stolen from Tsachy, but this is really the spirit of this course. Like, try to have fun. We are also here trying to have fun. We just find this material very nice and interesting, and we are always open to feedback, so do come talk to us if something is not working or something is working really well. We can do more of that. And so going ahead, now Shubham will take a deeper dive into the actual material. We'll start the actual material. And the first half again would be more on lossless, so we'll start our journey into the lossless compression.
Hi everyone, welcome to the class. So today it's a short lecture. I will speak for a bit, introduce what lossless compression is about. Right, so the plan for the first few lectures, as Pulkit described, is we will cover a bit of theory, some concepts from information theory. You will already start seeing some algorithms as we start with the theory. And you might have done other theory courses or seen theory in other classes. One thing I find very nice about information theory and compression is the theory is really useful. It's not some abstract thing. It applies to some very specific simpler settings, but those simpler settings are very prevalent in real life. Even like this Monday, I was something in my work, and I thought, can I compress this better than this gzip or zstandard is compressing it? And I just like wrote a short Python notebook, was able to determine no, there is a gap with just some very simple theory that you will learn in the next few lectures. So it's not very hard. There is no like very fancy math involved, but it's simple, but it's very interesting. It's very intuitive. You should have fun with that. So let's get started. Stop me at any time if you have questions. Okay. So there was a question before about what probability background do we expect. So you should be familiar with probability, random variables, expectation. Conditional probability will come in a bit later, sort of joint distribution of two variables. Yeah, that's really it. Expectation will come in a lot, so you should know what expectation is, what is a conditional expectation, that sort of thing. You don't need to know like sort of advanced probability, like Borel spaces, that sort of thing. No, just basic. First course in probability is what you need. Okay, so let's get started with very simple setting. You have a alphabet. So every probability space, you usually have an alphabet, right? So here the alphabet is just A, B, C, D. You have just 4 symbols in your alphabet. And we have a very simple distribution. We have all of them are equally likely. So each of them has a probability of 1/4, right? So what I do is I create a text file. I just independently sample among these with this uniform distribution. And I get a file, I sample 1 million symbols, right? So as you know from like the law of large numbers, what I would see is in the file I would have like around 250,000 A's, 250,000 B's, 250,000 C's and so on. So can somebody tell me what will be the size of this file on disk?
It depends what you choose to represent the symbols as. In terms of bits, like if you use 1 byte per symbol, then it'd be 8 million bits. But if you use 2 bits, because there's only 4 possibilities, and then that can make it 2 million bits.
Yeah. So the answer I got was it depends on how many bits you use per symbol, and a typical file, as we will see shortly, like a typical way if you write in Python and like just create this file, you would use 8 million bits or 1 million bytes, and we'll see why shortly. Thank you. So before we start about it, Pulkit talked a lot about like going up to even exabytes and zettabytes. But what is a bit? What is a byte, right? So this is just from the dictionary. So a bit is just a unit of information. expressed as either a 0 or a 1. For us, the way to think about bit is a bit is either 0 or 1. So it is like two possibilities, right? Every bit is a 0 or a 1. And those who are familiar with computers, you know, like bit is sort of the fundamental unit at which things works with semiconductors and transistors and so on. And a byte is a group of 8 bits. So 256 values, right? Each bit is 2 values. A byte can take 256 possible values, 2 power 8. Okay. So 1 byte is 8 bits, and then what? 1 kilobyte is 1000 bytes, which is 8000 bits, and so on. Just a warning that sometimes people use powers of 2 instead of powers of 10. So usually it's very close, but like in my work sometimes, right? So you have 1 exabyte. If you represent it as 10 power 18, that's one number. But when you represent it as 2 power 60, it actually starts to matter at very large values, whether you use powers of 10 or powers of 2. So just a warning, like when you're dealing with big numbers, be careful whether someone is talking, when they say kilobyte, do they mean 1024 bytes or do they mean 1000 bytes? Okay, so if you actually create this file, you check the size, what you would see is the size is 1 megabyte, 1 million bytes, and we are basically spending 1 byte per each symbol, right? A, B, C, D. And why? So many of you, I assume, are familiar with ASCII. ASCII is just an encoding. So when you need to represent anything in terms of bits, you need a way to encode it. So this is like a standard way to encode it. You can see a few of your favorite things here, right? Here you see like A through Z uppercase. Here you see A through Z lowercase. Here you see your numbers, punctuations here, right? And for each of those, like A is represented as 65, and then B is represented as 66. So it's just a way of representing all of these things we see on our keyboard as numbers and hence as bits. So like this is the ASCII table, for example, for ABCD, our alphabet, right? And you see we are using 8 bits for each of the values. Any questions? This is very simple. As Pulkit said, it will get progressively more interesting and complicated. Okay, so someone already answered this question, can we do better? And what they said was, yes, we can do better. Why? Because if you see here, this doesn't seem like, if you know that your file only has A, B, C, D, this doesn't seem like the best use of your bits, right? See this part is like the same for all 4, 1, 0, 0, 0, 0. So you just seem to be like wasting a bunch of bits for each of those symbols. To sort of explain what I mean, let's see this code, right? So what we are doing now is we just use 2 bits per symbol, right? 2 bits for every symbol. So if you have the same file of 1 megabyte, 1 million symbols, now it would use 2 million bits, which is 250 KB, right? So now it's like 250 KB instead of the 1 MB we were using before. Can someone suggest, like, if I use this code, are there any considerations? Like if I create a file using this code, right? I use 2 bits per symbol, and then I send this file to somebody, what do they need to know in order to read the file? Go ahead.
They need to know what symbol represents like what bits. So if they think that 00 is equal to D, then they won't be reading it right. So you have to send them the key and what each symbol means.
Yeah. Do others agree? Any other suggestions? Yeah. So the answer was, they need to know how to decode it. Basically, they need to know this table, right? In simple words, like if they have this table, they can decode the file. Like they receive this 0001 and so on. But unless they know that my 4 symbols were A, B, C, D, right? How do they know it was not E, F, G, H or 1, 2, 3, 4 or something, right? Just because they get the file, they can't that's why we use ASCII, right? That's the whole point of ASCII, that everybody knows what ASCII is. It's a standard thing. So when you send a file, they know it's an ASCII file, they can read it. And we will see a lot of compressors in the class, and every time you use a compressor, you need to indicate to the receiver basically, like what compressor did you use. You might have seen file extensions. Sometimes they play that role, like you have a .pdf or .zip or whatever. Okay, so I guess this should have been X, which is what we are using for the alphabet. So if you have K symbols, then you use log K bits in a fixed bit width code. Let me explain. So if you have 2 symbols, you just need 1 bit, right? Because 2 symbols means you have just 0 or 1, right? If you have 4 symbols, we already saw. For 4 symbols, you have like 0, 0, 0, 1, 1, 0, 1, 1. Right? If you have like 8 symbols, then you could do like 0, 0, 0, 0, 0, 1, 0, 1, 0, so on. What would I do if I had 3 symbols, let's say? How many bits do I need? Good.
2 bits.
2 bits. What are the 2 bits? Like how let's say it's just 1, 2, 3 is what I'm trying to encode. Can you suggest an encoding?
0, 0, 0, 1, 0.
Yep. Yeah. So that's one way, or you could, a bunch of possible things, doesn't matter really, like you could do. Okay. Any of the possible sort of combinations here. Right, so is this clear to everyone? Good.
Like the last line a little.
Ooh, I see. Okay. Yeah. Let me rewrite it here. 1, 2, 3. 0, 0, 0, 1, 1, 0. Or you could do like another encoding which is like this sort of thing. Lots of possibilities there. For the 3 symbol case, do we think this is like the best you can do? Or do you think we should be able to do better? I guess the person answered. Or go ahead, yeah.
Yeah, in this case, we should be able to do better because, for instance, we could have like one of them just starts with 1 and the other 2 start with 0. So you could have one of the symbols encoded with only 1 bit instead of 2.
Yeah. So the suggestion is that like nobody is forcing us to always use 2 bits per symbol, right? Maybe there are other schemes where we use different number of bits for different symbols. That's a good idea. There is another idea which you will actually see in the quiz today. That's a slightly different idea. Ultimately, it's a variation of the same thing. But yes, as you can see, like for 2 symbols, this seems like, okay, this is exactly right. Like you exhaust the whole code space in a way. For 4 symbols, this looks exactly right. For 3, already you start to see that like it's not trivial. Like you need to do some work to, because why are we using the same number of bits for 3 symbols and for 4 symbols, right? So clearly there is some inefficiency. So what you will see very soon is this fixed bit width code is not like a particularly good code in most scenarios. If you want to use the same number of bits for every symbol, very soon you run into like all sorts of limitations. And we will see like in a minute something better. Yeah. Good.
But if we don't fix bit for each code, like each letters, then how can we decode it? Like the length varies for each code.
Yeah. So the question is like if we don't fix the bit width, how will we even decode it? We will see a code later today, and I will ask you to actually decode it at home and come back to me in the next lecture. Yeah. There are ways. We'll figure it out together. Yes. But that's a valid point, right? Like one thing to like about the fixed bit width code is it's like trivial to decode. I give you a file with like, let's say you are using like you're using like a 3-bit per symbol code, right? And then I give you like a file of, like I give you some file like 000101110 whatever. You just like divide it into sort of sections of like 3, right? And then you can decode each of those. It's very simple to decode it. But the more complicated codes will be more complicated to decode also. Okay. So with this we already saw, right? Like if you have a uniform distribution, like each of these are equally likely, you spend 1 bit per symbol. This seems good. This seems optimal. We don't think this is like there is any issue here, right? Like obviously, like if A and B are equally likely, you should need to use 1 bit per symbol. Okay. Now, see, I slightly modified the distribution. Here you had just A and B, and both were like 50-50. Now I said, no, I have C and D also, but they have like lower probability, right? So what I'm saying is it's almost always A or B, but in very rare cases it can be C or D. This looks like a very similar distribution to the one we already had in the last slide. But now suddenly you see that if you use your fixed bit width code, you start to use like 2 bits per symbol. See, you already should start seeing some inefficiency, right? Like, no, clearly this is not like the best thing you should be able to do. This is so close to the previous one. We want to be able to use like basically 1 bit per symbol. Okay. Any questions so far? See, this is my genomics background coming in. In genomics, you have like base ACGT and accidentally wrote it anyway. Okay, so one solution which sort of was hinted by Pulkit, but which we won't really do now, is I don't care about C and D. If I see a C or a D, I will just encode it as A or B. It will only happen 2% of the time. Who cares, right? This would actually be fine in like some of the image and video compression parts because there what matters is human perception, right? You don't want to. You are fine with if 1 pixel changes, for example. And we'll see much more nuance there. But usually for text or logs or databases or PDF files or something, you don't want to lose any bit at all. It has to be lossless. That's the traditional way people do it. Maybe things will change. But lossless compression is important, not only because the application demands it, but also when you do lossy compression, you will see that the lossy compression is often built on top of lossless compressors. So the first half of the course will basically like provide you the foundation for the second half of the course. So we do want to losslessly compress it. We don't want to lose the C's and the D's, right? So actually, like some people have already suggested a solution, which is to use variable length codes, which we will now see. Variable length codes. This is like the key idea for today's lecture, really. This should be your takeaway. And let's see it here actually. Okay. So, simple idea. You have things which are more probable, you have things which are less probable. Let's use less number of bits for the more probable stuff and more number of bits for the less probable stuff, right? That's sort of obvious. You want to reduce your overall expenditure of bits. You want to make your file as small as possible. So let's do it. And we'll come back to the question that was asked about like how will you even decode it. Let's come back to that later. For now, like trust me that this can be decoded. So do we understand the code, right? So what are we saying is that A will be decoded as 0, B will be decoded as encoded as 10, C is as 110, and D as 111. So like let's say you had like A, C, D as your thing. After you encode it, what you will get is A will become a 0, C will become a 110, D will become a 111. Right? So hopefully that part is clear. Like the code just is a way to like you have a sequence of input symbols, you are able to encode it as a sequence of bits, right? And why do we use bits? We already talked about it because bits is the unit of storage on a computer, so you need to ultimately convert everything to bits. Right? Any questions so far? Okay. Right. So remember this idea, right? Really, this is takeaway for today. Fewer bits for more probable symbols, very obvious. Now, See, the last one we had like the previous code we were talking about was 2 bits per symbol. That was very simple to evaluate. You would just, it is using 2 bits per symbol. Here it's trickier, right? Here it's, for some symbols you're using just 1 bit. For some symbols you're using 3 bits. So is it better than the previous one? Can somebody suggest, like, how would you, first of all, do you think it is better than just using a 2 bits per symbol code? Good.
It should be better since like roughly half the time we're using 1 bit instead of 2. And then to evaluate it, you can just look at the bits per symbol, which is just multiplying the probability by the length for each of them and adding them together.
Yeah. So the answer was, which is correct, is you can say that half of the time you are using just 1 bit, right? So in this case, you are just using 1 bit, and here you are using 2 bits. So on average, you are like roughly using 1.5 bits per symbol, right? The other two we will ignore for the moment because they are very low probability events. So basically, you are using 1.5 bits per symbol instead of using 2 bits per symbol. Is that roughly clear, right? Like, because each of them, like A and B are really the things that occur more often, right? For A, you use 1 bit, for B, you use 2 bits, so it's on average like 1.5 bits per symbol. Let's make it precise, and then we'll come back to the intuition. Expected code length. So this is the measure we will use to evaluate all our codes in the first half, basically, of the course. So what is this? This is, one way to think about it is compressed size divided by uncompressed size. So how many bits you are using per symbol of input, right? On average, right? So there is an expectation floating around. Let's come to that. Okay, sometimes it is called compression rate, sometimes it is called compression ratio. Sometimes people use compression ratio to mean the reciprocal of this quantity. So lots of confusion. Don't worry too much about it. We will, whenever we give you a homework or a quiz problem, we will clarify what we mean exactly. But really what it means is the bits per symbol. Like this is sort of the way to think about it. How many bits you are spending per input symbol. So let's say you have a symbol X with code length LX, right? So in the previous slide, for example, A had a code length of 1, B had a code length of 2. So that sort of thing. And probability Px, then the expected length of a single symbol is this. This should be clear, hopefully. If it is not, if you think you have like, you need to brush up on your probability, let us know. We can find some resources, send it to you. But hopefully, this is very basic stuff. Hopefully, everybody is comfortable. Yeah. So for this code, like let's just compute the probability. Okay, so let's write the length down, right? So 0 is length 1, this is length 2, length 3, length 3. Hopefully this is clear. And then we just need to do like PA times LA plus PB times LB and so on. Can somebody do it for me? Good, yeah. Right, 1.53. Yeah, so a couple of students correctly answer 1.53, which if you recall now, like is very close to 1.5, right, which we expected already from our sort of back of the envelope calculations. Yeah, here is the full math. You will have some quiz questions if you need to brush up. You will get an opportunity. Yeah. So this is good, right? Like calculations aside, like we went from 2 bits per base, 2 bits per symbol to 1.53 bits per symbol. So that's good. We have one unanswered question, like can you decode it, which we will answer next time. So see, this is the point basically. Is the code lossless? So what I would suggest for next week, do this. I guess let me write something and then I will ask you to decode. Don't see me writing it because otherwise like you will know like what order I wrote it. Okay, let's say like So just decode this, and so next lecture we will see if we are able to decode it, right? And whether everybody decodes it to the same thing, or do we get 5 different answers? Yeah. Right. And we'll talk about this in much more detail next lecture. You will understand if you are able to decode it, why you are able to decode it exactly. There is a reason. Right. The other thing you should have seen is that the non-uniform distribution we saw, right? The 0.49, 0.49, 0.01, 0.01. It was worse in a way, right? Because you had 2 extra symbols. It wasn't as simple as the original one. Like I'm talking about these 2 distribution, like the AB and the other one we saw with the ABCD with the 0.49, 0.49, 0.01, 0.01. Right. So one thing you might have noticed is these 2 look very similar. And so you would expect that the optimal code, like the best you can do for both of these distributions, should also be similar. That's just intuitively, right? So right now we got from 2 bits per base to 1.53. That's not really optimal. And you will see it in a few lectures how you can actually achieve the best for this distribution, right? And you might think, okay, why do we care? It's a weird distribution. But as you will see later, right? When you have a video compressor going on and it produces some sort of intermediate thing, that can have any distribution, and you need to be able to encode any distribution optimally to get to the best results, basically. Right. So that's what we'll do for the next few lectures. So we will compute the optimal compression rate for this setting. We will show that it's roughly 1.14 bits per base, right? So it's not quite 1 bit per symbol. It's 1.14. And very interestingly, we will show that we'll show how to achieve this, and we will show you cannot do better than this with any scheme in the world, with infinite compute, whatever you do. If you want lossless compression, this is the best you can do for that particular distribution. That's one of the beauty of information theory, that you can prove these impossibility results. Any amount of compute, any thinking, even Albert Einstein, the smartest person on earth cannot compress it better than, because you can prove that you cannot do better than that. Yeah. So yeah, just remember your homework, decode it, and I will see you in the next lecture. Thank you. Happy to answer any questions.